Hello and welcome to this fifth module of our introductory course to subatomic physics. In this module we will discuss the structure of hadrons and strong interactions. In this first video we discuss the elastic electromagnetic scattering between electrons and nucleons, which is one of the ways used to study the structure of hadrons. After following this video you will know the main properties of elastic scattering between fermions and the meaning of the different terms that enter into the cross-section. The form factor concept you will know and its interpretation in terms of the size of the nucleon, and you will get to know the historic experiments at the Stanford Linear Accelerator Center in this area. When the structure of an interaction is known, it can be used as a tool to better understand the particles that are involved. We'll see in this video how elastic electron-nucleon scattering is used to determine the internal structure of nucleons. We take advantage of the fact that the electron, as far as we know, is a point-like particle and that we know electromagnetic interactions very well. We can thus elucidate a single but important unknown, which is the distribution and the dynamics of quarks inside the proton and neutron, represented by the big blue dot in the right diagram. We'll see in video 5.3 also how meson resonances are formed by an incident photon, for example. These can be used to better understand the strong force that binds quarks and antiquarks together. The prototype process for the scattering between point-like fermions is electron-muon scattering. It is very similar to E plus E minus annihilation with the Feynman diagram rotated by 90 degrees. We will approach this process in steps. The first step is already shown here, since we have encountered it in the past. It is to consider scattering of a very heavy target, which is without internal structure and without spin. Also ignoring the spin of the incoming electron and neglecting its mass, we obtain the formula shown here, the Rutherford cross-section, which we already encountered in video 1.4. As usual, the factor alpha squared comes from the two electromagnetic vertices. The denominator contains the square of the characteristic energy. It results from the propagator of the virtual photon, 1 over q squared, and you can easily verify this in the approximation that the mass of the electron is negligible, as I did here. The angular distribution is extremely steep for the scattering of point-like particles, and it peaks at small angles. This remains valid when including the effect of the target recoil and the spin of the particles. The additional term in red, shown here, with m the mass of the target, takes into account the recoil. It is the ratio between the incident and the outgoing electron energy E prime over E. This ratio is 1 for an infinitely heavy target, but less than 1 for an important recoil. This formula still neglects the magnetic component of the interaction. For a point-like fermion target with a magnetic moment mu equal E over 2m, one finds the complete Mott formula given on the bottom of the page, quoted here in the laboratory frame and for relativistic electron projectiles. The last term in red is of a magnetic nature. It becomes important at high momentum transfers q squared, much larger than the mass of the target squared. The angular distribution still roughly follows the form of the Rutherford formula. The third term contains subterms proportional to cosine squared theta and to sine squared theta, which reduce a little the steepness of the angular distribution. The historic experiments on elastic scattering between electrons and protons have been conducted at the Stanford Linear Accelerator Center in the 1960s and 1970s. The experiment consisted of a liquid hydrogen target bombarded by electrons of a few hundred MeV. In the final state, only the electron is observed in two spectrometers positioned at variable scattering angles. The kinematics of the hadronic final state is then deduced from energy momentum conservation, assuming a target at rest. Here are some results on the cross-section as a function of the scattering angle on the left and as a function of the incident electron energy on the right. The measurement confirm the calculation at these modest energies already below 1 GeV. One observes a steep angular distribution in the left plot and a strong reduction of the cross-section with energy in the right plot, as we expected from the formula. Let us now consider what happens if the target is not a point-like particle. Let us first take the model of a static charge distribution, rho of x, normalized such that the charge of the target remains elementary, which means that the integral over rho of x must be equal to 1. The cross-section then will be reduced with respect to a point-like target by a factor of f squared, a so-called form factor. We have already used this concept in video 2.2 when we discussed the size of nuclei. In the static case, it is simply the Fourier transform of the spatial charge distribution. For small momentum transfers, one can develop the form factor in powers of q times x. If the distribution possesses spherical symmetry, that is, rho of x is only a function of r and not of the spatial directions separately, terms with odd exponent will not contribute. Thus, the form factor measures the mean square radius of the charge distribution, r squared mean, which represents the size of the distribution. Take, for example, an exponential distribution as a function of distance. It leads to the so-called dipolar form factor that is shown on the last formula on the right. It is clear that in the case of a non-static charge distribution, things get more complicated. First, magnetic interactions come in, since the target is moving. Second, the charge distribution itself changes during the time represented by the time-like component of the four-momentum transfer q0. By the action of moving charges inside the distribution, electric and magnetic terms will be modified and their functions will in fact be mixed up. We then find the cross-section given here with a parameter tau, which is the ratio between the momentum transfer and the target mass squared. The ratio of the two quantities which characterize this process. We call GE and GM the electric and magnetic form factors, although the distinction between the two obviously depends on the reference frame. In the same sense, one can attribute GE and GM to the Fourier transforms of the charge and magnetic moment distribution of the target particle, even though this interpretation is strictly speaking only valid in a very special reference frame. The form factors GE and GM of the proton are measured by analyzing the differential cross-sections for the reaction E minus P goes to E minus P, and separating the terms proportional to cosine squared theta and sine squared theta of the angular distribution. We observe that GE and GM follow the dipolar shape predicted for exponential charge distributions. The parameter lambda then characterizes the size of the distribution, and we find lambda equal to 0.84 GeV in both cases. The size of the distribution is thus of order 1 Fermi, and the same for electric and magnetic form factors. Finding the same distribution for both form factors is not a miracle. The quark inside the nucleon are at the origin of both charge and magnetic moment distributions, such that we find the same distribution because they are caused by the same ingredient. The figure shows representative results obtained by Hofstetter and collaborators at SLAC in the 1960s. The form factors GE, shown on the left, and GM, shown on the right for the proton, are measured as a function of the momentum transfer squared and extracted from the cross-section for the elastic electron-proton cross-section. One finds the dipolar shape, G equal to 1 over 1 plus q squared over lambda squared, both squared, with the same size parameter lambda equal to 0.84 GeV. In the next video, we will see what happens when we increase q squared such that the exchanged photon can excite or even break the nucleon.